All right, here we are for AP Physics, Work Kinetic Energy Theorem 2, Problem 5. It says, if it takes work W to stretch a Hooke's law spring a distance D from its unstressed length, determine the extra work required to stretch it an additional distance D. That would be like from position D to position 2D. So I'm going to do this probably a couple ways, but here we go. I'm going to start by doing this graphically, okay? This is the way that I would have shown this to you last year. We said, hey, look, here is our force of the spring versus position graph. And if this is a Hooke's law spring, we remember that this gives us a nice linear relationship via the equation force of the spring equals negative k times the stretch length, right? Now, we're going to go ahead and take this guy, and we're going to stretch it from x equals 0 to, let's say here. We'll say that that is D, right? And then we're going to stretch it from D to 2D. There. You say, now look, right here, the area under the force position graph, you say, that's the work done. So we'd say, hey, that is the work done by the spring, which they told us that is W. They want to know how much work is done when we go from D to 2D, right? So they want this area, right? Okay. Well, there is a nice relationship there, okay? And you may even remember this from last year vaguely. Here we go. Look, as I go along distance D, the force gets bigger by a certain amount. There's a certain slope here, right? Rise over run. Hey, it's that same slope here. Same horizontal distance, same horizontal rise. So this here, this height is the same as this height. This triangle is congruent to that triangle. And this height is always the same. If I split this in half, you're like, oh my gosh, look, 1, 2, 3 of these triangles. So the work done from D to 2D, this area is in fact 3W. That is the short version, all right? Okay. Now, if I go ahead and I slog through this thing the long way, all right? Sorry. Here's the shortcut. The long way looks like this. Hey, the work, all right, I know is going to be my integral. For the first part is going from 0 to D of that force of the spring dotted with the distance. The force of the spring is going to be like, kx or whatever. I'm just going to, not worry about the sign, if that's all right with you. Kx, cosine 180, whatever, is going to make this a negative, right? When I do cosine of 180, because that force of the spring is against the motion as I'm stretching the spring, right? So that's going to give me a negative 1 when I do the cosine 180 dx from 0 to D. If I go ahead and I do this, integrate this is going to be minus k times the integral of x dx. That's going to be a minus 1/2 kx squared. Sorry. K of the spring, right? X squared, right? Anyway, evaluated from 0 to D, plug the D in for x. That'll be a 1/2 k d squared minus, when I plug a 0 in, oh gosh, that's just 0. So 1/2 k d squared, that's the work done by the spring when I stretch it D. If I go now and I calculate the work going from D to 2D, okay, so this was like, I should have color-coded this. That was silly of me. This is the green calculation, right, for this. Now let's do the orange calculation. Well, the orange calculation would be the work going from D to 2D, right, of that f dot dx. Yes, that's going to be kx negative 1 dx, right? I'm taking the absolute value. That's why there's no negative x. Take the absolute value, okay? And to 2D, and you say, yes, that's going to be a minus 1/2 k x squared evaluated from D to 2D, right? When I go ahead and this is my work going from D to 2D, all right? You know what I'm saying? Anyway, when I go ahead and I do that, that's going to be plugging in a 2D in for x, right? That'll be like negative 1/2 k, and that'll be 4d squared, right? Minus plugging in a d there, minus 1/2 k times d squared. All right. All right. There's negatives in both those terms. It's because it's a negative work term. Let's just factor that negative out of this mess. Okay. In fact, you know what I could? No, just factor the negative out. Now we'll leave it. Yeah. Let's just work it out. If I do this like minus and a minus, is going to make this a positive. So I'm going to add a 1/2 kd squared to a minus a half, like 4 kd squared. Do you see that's going to be equal like minus a half, but instead of 3d squared minus a 1d squared? You know what I'm saying? It's going to be 3d squared. Do you see that? Now look, how does that work going from D to 2D compare to the work going to D? You say, look, they're the same except this is a 3. This is 3 times that. So the work going from D to 2D is 3 times the work at D, which they just called W, so I should just let that alone as W. The point is it's triple. Okay, so the work there is triple. That was it. That's problem 5. And again, you say, yeah, it makes sense because the force I'm having to pull against is bigger than it was here, right? So I'm going to be doing more work because I'm having to pull with a greater force through this whole bit in here versus here. Yep. All right.